One of the applications of all of the electricity and magnetism that we've studied is in electromagnetic radiation, which is really just light. Being able to describe light with our electromagnetic equations turned out to be really just a resounding success of Maxwell's equations. And you've seen part of Maxwell's equations here. So we've got Gauss's law, which you know, which says that the electric field depends on the charge enclosed. There's a version of Gauss's law that we haven't talked about, this one for magnetic fields. All this says is that the reason there's a zero here is there is no North Pole without a South Pole, or vice versa, because there's no individual magnetic charge. So because we haven't found any individual magnetic charges, this is our version of Gauss's law for magnetism. Faraday's law, this is going to look a little different. You've seen that you have an EMF is equal to the changing flux, or an EMF is a voltage difference, which comes from when we were developing this idea of a voltage, we took E dot a displacement. And then there is the way you actually derive the equations for the magnetic fields is we can create something that's like Gauss's law called Ampere's law, which says that the magnetic field that you get is due to an enclosed current inside a magnetic or an Amperian loop. And so basically what these laws on the right, Faraday's law and the Ampere-Maxwell's law, say is the following. So Faraday says a changing magnetic field causes actually an electric field, which is what gives us a voltage difference. Ampere's law says that we can create, and Gauss's law also says we create electric fields with charges. Ampere's law says we create electric fields with current, make magnetic fields with currents, and our right-hand looping rule, but it also says a changing electric flux or changing electric field can cause a magnetic field. So now we have, and that's Maxwell's addition, a changing electric field, changing electric flux, gives us a magnetic field. Now, we're not going to calculate all of these, any of these at this point. I just want to set this up. So this is Maxwell says that, and just for reference, Gauss says charge gives us electric field, and Ampere says that current, moving charges, give us a magnetic field. Okay. The important thing here is to look at these two relationships, because what can happen is that we can get a changing, so we have a magnetic field that changes, it goes up and down or left and right, whatever it does, but if that changes, then it causes a changing electric field, but then a changing electric field causes a changing magnetic field, and this loop feeds back on itself, and it can go on forever. And that's what we call a light wave. A light wave is electromagnetic, because it's the interplay of changing magnetic and electric fields, electromagnetic wave. And so what happens in an electromagnetic wave is you set up a charge like this, a plus charge or a negative charge, you make it go up and down, and that changes the electric field. So the electric field goes up and down, and then the changing electric field it turns out that it's perpendicular to, because of all of our right-hand rules, gives you a changing magnetic field. So this might be your magnetic field, and this is your electric field going up, up and then down, and the magnetic field coming in and out of the page, all while your wave is traveling like this. And that's the direction that electromagnetic waves travel, and the speed that they travel, if you do the calculation, turn this into a wave equation, the speed that they travel is given by c, the speed of light. So let me show you what this looks like in a simulation. So here's a charge, and I'm going to have it oscillate. And you can see that these are electric field lines. So this in the middle, the red dot, is an electron or a proton, and it's moving up or down, and it's creating these electric field lines, and they're waving. So this is just showing you the electric field, sort of like I drew before. And then from that electric field, you get a magnetic field, but because this magnetic field changes, you then get you get an electric field, and it goes on forever. And it goes on until this wave runs into something, like your eye. And so this is light, radio waves, so it's light, visible light, radio waves, X-rays, microwaves, all of these are electromagnetic radiation. And we'll look in the next video about some of the properties of these.